All right, in our last section talking about limits, we're going to talk about infinite limits. Limits at infinity, limits that are infinity. So when we say limits at infinity, what we're really trying to find is we're really trying to find out where the graph approaches as x gets very large or very small. So that's basically as it goes to infinity or negative infinity. So negative infinity would be a really small number. Gets really, really negative. Or infinity would be a really, really, really large number. So we typically say large numbers are infinity, small numbers are negative infinity. Now earlier this year we gave this a different name. We called it the end behavior. So we said as x gets really large or very small, where does the graph approach? We called it end behavior. So when we look at these two types of limits, when we're looking at limits at negative infinity as x approaches infinity or negative infinity of the function, we're really just looking for end behavior. And if you remember when we were looking for end behavior of a lot of things, when we're trying to plug in infinities or negative infinities, we're really trying to find the location of any horizontal or oblique asymptotes. We're trying to see if these graphs approach anything as x gets really, really, really large. So there are really only three cases of trying to find these horizontal or oblique asymptotes. The first one is the degree of the denominator is larger, we'll say greater than the degree of the numerator. So an example of this might be the limit as x approaches, we'll say positive infinity, of x plus 2 over x squared minus 3. So the degree of the top is 1, the degree of the bottom is 2. So the bottom is bigger than the top. These limits at infinity, the end behavior we said always had a horizontal asymptote of 0, so the limit is always 0. So this always has a limit as x approaches positive or negative infinity. Any function of this form will always give us 0. So if the bottom's bigger, automatically 0. Let's look at the second case. We'll just do the opposite. Let's say the degree of the denominator is less than the degree of the numerator. So an example of this might be the limit as x approaches infinity of x squared plus 2 over x plus 3. Okay. Now, when the degree of the top is bigger than the bottom, the limits at positive or negative infinity will never be actually a number. And generally, these will always turn out to be either positive or negative infinity. So if the graph goes off to infinity, as it kind of increases forever, then it's going to be infinity. If it goes down forever, then it's going to be negative infinity. This can be very easily seen with a graph. So this graph at the end is going to look something like this. It's increasing this direction. On the other side, it's decreasing in this direction. It just kind of does some different things. So as x approaches positive infinity, the limit is infinity. As the limit approaches negative infinity, as x approaches negative infinity, this graph approaches negative infinity. So we can say the limit of this case, x approaches either positive or negative infinity. If the top is bigger, will always be either a positive or negative infinity. And we'll talk more about positive and negative infinity limits here in a bit. The last case, of course, is if they are equal. If they are equal, so let's say the limit as x approaches infinity of 3x squared minus 2x plus 1 over x squared minus 4x plus 2. Well, in this case, all we have to do is we can actually rewrite this limit. And this is actually, you can actually do this for any of them, but for this one it becomes really powerful. We circle the ones that have the highest degree or the highest power, which is 3x squared over x squared. Those are the highest power in the top and the highest power in the bottom. So if we rewrite that, we can rewrite this limit as 3x squared over x squared. Well, in this case, I can simply cross those x squareds out, and I just have the limit as x approaches infinity of 3. this will just equal 3. So if the bottom is bigger, it's always 0. If the top is bigger, it's going to go off to infinity or negative infinity, depending on the graph. And if it is actually equal, the degrees are equal, then we just divide, and we typically will get just some real number. Just some kind of things to look out for. Make sure the exponents are in order, because we do want to get the highest power. If any of the leading coefficients are negative, that might influence where the graph is going. Remember, all these you can graph and see whether they're going to infinity or negative infinity, things like that. And when you are plugging in negative infinity, do you get a positive value? For instance, when you square negative numbers, you always get a positive, even infinite numbers. Okay, so let's look at some examples of looking at limits at infinity. So this first one, I look at it saying, what is the limit as x approaches infinity of x squared minus 3x plus 2 over 4x squared plus 5x minus 1? Well, the degree of the top is 2, and the degree of the bottom is 2. So we're actually going to look at those two leading terms, x squared and 4x squared. So when they're equal, we said we could rewrite this as the limit as x approaches infinity of x squared over 4x squared. Well, these cancel, the x squareds cancel, and this will just leave me with 1/4. So this graph has a horizontal asymptote at infinity of 1/4. So if you look at the graph, as it gets really, really large, gets toward the ends, it's going to approach 1/4. Okay, let's look at number 2. Now number 2, let's look at the degree of the top. The highest power is 1, it's negative 5x. The degree of the bottom is 2, because 2x squared. So this is degree 1, and this is degree 2. This is the easiest possible case, because if the bottom is bigger than top, the limit at infinity or negative infinity automatically 0. So that's like best case scenario. So equal, you divide them out, get a real number. If the bottom is bigger than the top, automatically 0. Now the last two cases fall into our third case, which basically is the top is bigger than the bottom. And we said these have to basically go to either infinity or negative infinity. So I'm going to show you a real easy way to figure out where these limits go. So this first limit, the top is bigger than the bottom. But we said that we can rewrite this as the quotient of the highest powers, which would be these two. So if I rewrite this as the limit as x approaches infinity, I'm going to rewrite this as 2x squared over 3x. But what you can see is I cross out one of my x's. So this will be equal to the limit as x approaches infinity of negative 2x over 3. So now basically what we're trying to do is we're trying to take a negative number, because it says negative 2/3. So if I take negative 2/3 times the largest positive number, because it's infinity, what am I going to get? So what I'm thinking of, a negative number times the largest positive number ever in existence will actually equal a negative infinity. And what this negative infinity really means is if I look at this graph at its end behavior, essentially it's going, wrong way. It's going down as x goes to infinity. So as x gets really big, so this is x increasing this way, it's saying the y value, the function's going to negative infinity. So if you graph this function, if you were to put negative 2x squared, blah, 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 over 3x plus 2 into Desmos, let's say, and look at it as it goes off to infinity, it will dive down and kind of go toward negative infinity. Let's look at number 4 and use a similar technique. Highest power here is negative 2 and 3x, basically the same problem, but you can notice this one goes to negative infinity. So if I rewrite this one as the quotient of its leading terms, it's going to be negative 2x squared over 3x, where we can cancel one of the x's. So this is the limit as x approaches negative infinity of negative 2x over 3. So now we're taking the largest, our negative number times the largest negative number ever. Well, negative infinity, a negative super big number times negative 2/3 will just equal positive infinity. So what that tells me about this graph is the graph is going to kind of go this way. Because as x's are getting negative, going more and more negative toward negative infinity, you can see the function, the graph of this function is going this way. I don't really know what the rest of the graph looks like. I could graph it. I could use some other techniques to see what it is. But right now, all I care about is what happens at infinity or negative infinity. So the last thing we're going to talk about is infinite limits. And these are essentially when the graph approaches an asymptote, graph approaches a vertical asymptote. So we know vertical asymptotes are these lines that the graph really can't cross. It just kind of goes up forever or down forever. So as the graph approaches a vertical asymptote, it approaches positive or negative infinity. So let's just draw a little picture. This is just some random graph. So let's say I have a vertical asymptote here. And here's my function. Let's say half of the function goes like this, and half of the function goes like this. Well, you can see that one part of the graph, as it gets really close coming from the left, it seems to be going to positive infinity. Now as the graph goes from the right, it seems to go to negative infinity. So at the asymptote, they go different directions. So in this case, you'd have a left-hand limit and you'd have a right-hand limit, which are different, which means the limit at the value actually doesn't exist. They could also go the same way. They could both go up to infinity. They could both go down to negative infinity, in which case you would have a limit that exists. So in general, we use a really easy principle to do infinite limits. We use this, what's called the infinite limit theorem. So the infinite limit theorem says if you plug in a value a into a rational function and you get any number over 0, then the answer is always going to be positive or negative infinity. Okay? So if you ever plug in and you get some number, any number over 0, then I know my limit is always going to be either positive or negative infinity. So the way we can figure out whether it's positive or negative, we can find the numerator by substitution, and then we can find how the denominator approaches 0. So either going to be negative or positive as well, and then we'll use division rules. So essentially, a positive divided by a positive is positive, a negative divided by a negative is a negative. So let's look at an example of how this works. So this says I want to know what is the limit as x approaches 5 from the right, and that's important, from the right, of x plus 2 over x minus 5. So the first thing I'm going to do is I'm going to plug in 5. You know, the first thing we always do is plug in just to see what we get. So if I plug in 5, I get 7 over 0. So right away I know my limit is either going to be infinity or it's going to be negative infinity. That's going to be my answer. I guarantee it. So what I'm going to do is I'm going to really try to figure out what happens to the bottom. So I'm going 5 from the right. So 5 from the right are going to be numbers slightly bigger than 5. So what's a number slightly bigger than 5? Let's say 5.0001. That's slightly bigger. So if I plug this number in, I'm going to get 7.0001. 5.0001 minus 5 is going to be 0.0001. Now the only thing I really care is if I take this number, 7.0001, and divide it by 0.0001, is it a positive or a negative number? Well, in this case, it is a positive number. So I know my limit has to be positive infinity. Anytime I get a real number over 0, I know the limit's either positive or negative infinity, so all I have to really figure out is if it's positive or negative. Now, if I sketch this graph, I'll just kind of sketch it here so you can see what it looks like. I've graphed it on Desmos. I don't have a picture of it here, but I know it has a vertical asymptote here, this kind of invisible line. So what I can see from this graph as it comes this way, it looks something like this. And as it comes from this way, it looks something like that. Now in this case, we were coming from the right. So as I approach from the right, as I approach 5 from the right, what happens to the graph? Well, you see it's going up to positive infinity. It's going up. Well, that's exactly what we said. If we said coming from the left, it would be negative infinity. So if you graph it, it's a great way just to check, make sure that it's going the right way. But using the division rule is not too tricky. Okay, let's look at the second one. Now you got to be careful because you notice this one, it does have a squared. So if I first plug in the 2, I get 4 over 2 minus 2, which is 4 over 0 squared, which is 0, which is 4 over 0. So right away I know this is going to be either positive infinity or negative infinity. I just got to figure out which one. Now it doesn't really say which way I'm coming from. It doesn't say from the left or from the right, so I'm going to do both ways. So first I'm going to look at the limit as x approaches 2 from the left. So that's numbers slightly smaller than 2. So maybe like 1.99999. Well, if I plug in 1.99999, I'm going to get 4, because that doesn't change. 1.99999 minus 2 is going to be negative 0.01 squared. But if I take a positive number and divide it by something squared, remember this square term is always going to be positive. So I have a positive divided by a positive, so I know my answer has to be infinity. Now that's coming from the left. So if I do from the right, so 2 from the right, a number slightly bigger than 2 might be 2.0001 of this function. So if I plug that in, I'm going to get 4 over 0.0001 squared. But with the squaring, that's going to give me the same thing. So both of these equal infinity. So coming from the left equals infinity, coming from the right equals infinity. So the limit is infinity. If I graph it, you can see what it looks like. If I look here, it's at 2, has a little asymptote like this. But the graph looks something like this. So this is what your graph looks like. So you can see from both directions, the graph is approaching positive infinity because it's going up this direction. Okay, let's look at a couple more examples. So this first one says limit as x approaches 2 from the right of x squared plus 4x plus 6 over x minus 2. So since it's from the right, I'm going to try to find a number that's super, super close to 2. Well, first let's plug in 2, just to make sure it gives us what we want. We know there's 0 on the bottom. And on the top, it's going to be 4 plus 4, which is 8, plus 6, which is 14. So right away, just based on that, I know it's either going to be positive or negative infinity for my answer. So if I take a number that's slightly bigger than 2, because this is 2 from the right, and I plug it in, I'm going to get some positive number, 14-ish, right? We don't really care what the top is. We know it's positive. That's all we really care about. Now the bottom, if I take 2.001 and subtract 2, I'm going to get 0.001. But I've got all the information I need here. I have a positive divided by a positive, so my limit's going to be positive infinity. Now again, all this just happens at asymptotes. If it's a number, like if I plugged in 2 and I just got 14 over 2, then the limit's 7. There's nothing fancy about it. It's only when you get this number over 0 do you get one of these infinite limits. Similar here, this last one says, what is the limit as x approaches 2 from the right? Well, if I plug it in, I get 4 minus 8, which is negative 4, minus 21, which is negative 25. So I get a negative number on the top. That's important. Over 2 plus 7, which is going to be 9. Now I got no 0 on the bottom, you notice. So my limit is just done. My limit is just negative 25 over 9. So you don't want to get too caught up to saying it's always infinity or negative infinity, because if you plug a number in and it's just some value, it's just some number, then that's your limit. All right, so hopefully this is helpful. Nice little introduction to infinite limits. If you have questions, please let us know.